Okay, for what we're going to be looking into, we have among the topics what is referred to as the adjoint of a matrix. And this will be a synthesis of exercises where you're looking at cofactors of square matrices as well as determining the transverse of a matrix, where you have those items put together. And we have, if you recall, we have with the cofactor where we have designated with the subscripted variable, we have C of ij, I in reference to the row number, j in reference to the column number, where we have the cofactor to be -1 to the I plus j power times the determinant of the matrix, which again was formed by deleting the ith row and jth column of A. And we have for the matrix of cofactors of A, you're going to have this general form, and we'll be getting into specific cases. And we have with the adjoints, you'll be looking at taking the transpose of this particular matrix. And so we have with this general form, so you have like the first row becomes the first column and vice versa. And we have you have ADJ with A in the parentheses. That is used in denoting the adjoint of matrix A. And we have just a case here where we have a square matrix, and just starting out with the 2x2 example, we had the matrix A consisting of 1 and 2 for the top row, 3 and 4 for the bottom row. And if we look for what we have with the cofactors, okay, so we have with the first row and the first column, okay, you have -1 to the I plus j, where both I and j are at 1, and you have times what we have with the element 4. So again, we have covering up the first row, first column, we have exposed the number 4. And we have for the cofactor of the first row, second column, again, covering up the first row, second column, we have exposed the number 3. And we have -1 to the third power, it becomes -1. And we have times 3, which comes out to -3. And then for the cofactor of the second row, first column, okay, you have second row, first column, we have exposed the number 2. And again, we have -1 to the third power, which is -1 times 2, so we have it -2. And then we have with the second row, second column, the cofactor, we have -1 to the 2 plus 2, which is going to be -1 to the fourth, which is +1. And we have times 1, okay, so that result comes out to 1. So the matrix of cofactors, okay, we're going to have 4, -3, -2, and 1. And for the adjoint, if I take the transpose of this matrix of cofactors, what I'm going to have here is that the adjoint of A is going to be where the first row is going to be 4, -2, and the second row we have at -3, 1. Now, let's say that for what we have, where we have a 3x3 matrix. Okay, so we have, for this one, we have the top row consisting of -1, 3, and 2. Middle row, we have 0, -2, and 1. And the last row, we have 1, 0, and -2. Now, looking at the cofactors, okay, for the first row, first column, again, you have -1 to the 1 plus 1, and you have times the determinant. Okay, so if you cover up the first row, first column elements, you have exposed -2 and 1, 0, -2. And so -1 squared is 1, and the determinant is 4. 1 times 4 comes out to 4. For the first row, second column, again, if I cover up the first row as well as the second column, I have 0, 1, 1, -2 exposed. And we have for -1 to the third, that is -1 times the determinant of 0, 1, 1, and -2. So we have -1 times -1 comes out to +1. And for the first row, third column, again, we have -1 to what is going to be the fourth power, which is 1. And we have covering up the first row, last column. Again, I have 0, -2, 1, and 0. And so this will translate to +1 times what's going to be +2 comes out to 2. And following in line, okay, so we have with second row, first column. So we have covering up the second row, first column elements have 3, 2, 0, -2. And again, we have -1 to the third is -1. times the determinant value of -6, and that product ends up at 6. And for the second row, second column, again, I have left exposed -1 and 2 at the top, 1 and -2 on the bottom. And again, -1 to the fourth is 1, and we have 2 minus 2 comes out to 0. And for the second row, third column, for what we have in covering up, what we have here, okay, so you have left exposed, have -1 and 3, as well as 1 and 0. And -1 is going to be to the fifth, which is -1. The value of the 2 by 2 determinant with the elements we have at -3, and the product we have at +3. And just following in line, working with the last row. Okay, so we have for the cofactor of the last row, first column, okay, that utilizing the same process, okay, the outcome comes out to 7. And for the last row, second column, the cofactor comes out to +1. And then for the last row, last column, we have, again, applying the same procedure, and we have that cofactor value to end up at 2. And utilizing these values, okay, and going row by row. So the matrix of cofactors, again, we're going to have it 4, 1, 2, followed by 6, 0, 3, and then we have in the last row, we come out to 7, 1, and 2. And so the transpose is going to be the adjoint, okay, which in this case, we're going to have 4, 6, 7, 1, 0, 1, 2, 3, and 2. Now, arriving at the value of the adjoint. Now, if we use adjoints to determine the inverse of a matrix by using an adjoint, and we have with the theorem that if A is an n by n invertible matrix, then the inverse is going to be the reciprocal of the determinant of A times the adjoint of A. And just some specific cases here in finding out what the inverse is going to be by using the adjoint. Okay, so going back to our first matrix, which we had a 2 by 2 with 1, 2 at the top, 3 and 4 on the bottom. Again, we're now going to have the determinant of A to be, again, have 1 times 4 is 4, minus 3 times 2, so we have 4 minus 6 is equal to -2. And again, just going back to the adjoints from earlier, again, okay, just repeating, so we have 4, -2, -3, and 1. And we have our tools at hand. So we have for the inverse of matrix A, you're going to have 1 over the determinant of A times the adjoint of A. And again, the determinant we have at -2. So we have 1 over -2, or -1/2 of the adjoint of A. And so taking -1/2 of each of these elements, and it's going to turn out that the inverse matrix will consist of -2 and 1 in the top row, and in the bottom row will be the elements 3/2 and -1/2. Now, looking at going back to what we have with the 3 by 3 matrix, and if we look at the determinant, okay, and again, you have your alternating sign pattern, and again, so you have like your plus, minus, plus, and if we look at it working with the top row elements and taking the cofactors, the minors, all that, so you have like plus of -1 times the determinant of what we have of the exposed elements with -2 and 1 at the top, 0, -2 on the bottom. Then we have -3 times the determinant of what we have with 0 and 1 at the top, 1 and -2 on the bottom. And we have +2. And again, taking the minor of the first row, last column, so we have 0, -2, 1, 0. And so we have here, we got -1 times 4, -3 times what's going to be -1. And we have +2 times what's going to be +2. And so we have -4, and what's going to be +3, +4, and we have for the value of the determinant of matrix A to end up at +3. And again, just going back to the adjoint of this matrix, again, we have 4, 6, 7, 1, 0, 1, as well as 2, 3, and 2. And looking at the formula for determining the inverse of a matrix using the adjoint of matrix A. So again, we have 1 over the determinant of A. This is going to be 1/3, and taking 1/3 of the elements in the adjoint of A. So you got 1/3 of all this, and so we have this 3 by 3 matrix where we have in the mix non-integers, And we have the top row consisting of 4/3, 2, and 7/3. Middle row we have 1/3, 0, and 1/3. And we have in the last row capping off, we have 2/3, 1, and 2/3.